Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized pieces.
Today, we're diving into the world of AI that writes. We all interact with it now, whether it's chatbots, story generators, or email assistants. But have you ever wondered how they actually produce that text?
It's a great question. For a long time, the dominant method has been something called autoregressive generation. It's a fancy term for a very simple idea.
Exactly. Think of it like writing a sentence one word at a time, from left to right. To pick the next word, the AI looks at all the words that came before it. The cat sat on the, and then it predicts mat. It's very logical, very sequential, and it produces really high-quality text.
But it has one major drawback. It's slow. Because it has to generate word by word, it can't really do things in parallel. It has to finish word one before it can even think about word two.
Which brings us to the new kid on the block, diffusion models. If you've seen AI image generators, you've probably seen diffusion in action. You start with a noisy, blurry mess, and the AI gradually refines the entire image at once, step by step, until a clear picture emerges.
Researchers have applied that same idea to text. Instead of a blurry image, you start with a sentence full of mask tokens or just random gibberish. The model then refines the entire sentence in parallel over several steps until it becomes coherent English. The big selling point? It has the potential to be way, way faster.
And this is where today's paper comes in. It's titled Scaling Beyond Masked Diffusion Language Models. The authors point out that diffusion isn't just one thing. It's a whole family of different techniques, and everyone in the field is trying to figure out which one is the future.
For a while, there's been a clear frontrunner, a type called masked diffusion, and the reason it's been the frontrunner comes down to one key metric that researchers love: perplexity.
Perplexity sounds complicated, but you can think of it as a model's confusion score. A low perplexity score means the model is very good at predicting the next word in a sentence. It's not easily surprised or confused. A high score means it's struggling.
And on this metric, masked diffusion models, or MDLMs, are the champions. They have the lowest confusion, the best perplexity. So case closed, right? MDLMs are the best, and we should all focus on them.
Well, that's the exact idea this paper wants to challenge. The authors argue that perplexity is an important metric, but it's not the only metric. It can even be misleading when you're comparing different types of models.
It's like judging a car only on its miles per gallon. That's useful information, but it tells you nothing about its top speed, its acceleration, or its safety rating. You need the full picture.
Exactly. So the researchers decided to look at the full picture. They didn't just look at perplexity, they looked at the trade-off between quality and, crucially, speed. How fast can these models generate text? They call this the speed-quality Pareto frontier.
That's another technical-sounding term, but the idea is simple. Imagine a graph where one axis is quality and the other is speed. The frontier is the line of best possible options. For any model on that line, you can't get better quality without sacrificing speed, and you can't get more speed without sacrificing quality. They are the most efficient choices.
So the researchers pitting a few different models against each other. First, the old-school autoregressive model, or AR, then the perplexity champion, masked diffusion, or MDLM, and they also included two other diffusion families, uniform state diffusion, which they call DUO, and an interpolating model called SOLM.
And when they plotted them on this speed quality graph, the results were really surprising. The classic AR model, the one word at a time guy, was the slowest, but it produced the highest quality samples if you were willing to wait. No shock there.
But in the world of diffusion models, the perplexity champion MDLM wasn't the clear winner in practice. In certain speed brackets, specifically for generating text really, really fast, the Duo model was actually the best choice. It dominated the high-speed end of the spectrum.
So even though Duo had a worse perplexity score, a higher confusion score, it was a more efficient and practical choice if what you cared about was getting good text out quickly.
But the biggest bombshell came when they scaled these models up to 1.7 billion parameters and tested them on a benchmark for math and reasoning problems.
This is a really practical test of a model's abilities.
And who came out on top?
It was Duo. The model with the worst perplexity score actually outperformed the classic AR model and the perplexity champion MDLM on the math and reasoning test.
Wow, so the metric that the whole field was using to crown a winner, perplexity, was pointing in the wrong direction, at least for this specific practical task.
That's the core finding. Perplexity is useful for comparing models within the same family. If you have two masked diffusion models, the one with the lower perplexity is probably better. But when you compare a masked diffusion model to a uniform state model like Duo, perplexity doesn't tell the whole story because they work in fundamentally different ways.
One might be a better test taker while the other is a faster sprinter. You need to know what race you're running.
And that's the big takeaway from this paper. It challenges the community to look beyond a single simple number. The authors show that models with worse perplexity scores can be faster, more practical, and in some cases, even better at complex reasoning tasks.
It suggests the future of AI language models might not be a single king, but a diverse set of specialized tools. You might use one model for a quick, real-time chatbot conversation and a completely different, slower model for carefully composing a long-form essay.
It's a reminder that in the messy, practical world of AI, how you measure success is everything. And sometimes the underdog model might just surprise you.